Okay, continuing on with talk number 2 in the final presentations for the astrophysical observations and instrumentation and techniques class. Next up is Jake Lange, who will be talking about how far we can see using gravitational lenses.
All right, thank you, Dr. Feig, for the introduction. This talk will be describing the use of gravitational lensing looking at the early universe. The kind of summary goal for this project is in the title: how far can we see, and how can we see it? Which I hope to answer, at least crudely, in this project. So just an outline of the project. I'll start with the goals, the questions I'm trying to answer, and then a little bit of background on gravitational lensing, and some motivation for why we use it looking at the early universe, and the state of the research, what it is now. A couple papers that were published in the last year that have given some insight as to the state of looking at the early universe. And then I'll talk about my data, the observational data I got that was based off Lange et al. 2014. I'll talk about the reduction that was done to that data, and then I have a couple graphs that show basically answering the questions: what wavelength should we look at, how should we look at the early universe, and what objects we should look at what redshift. And then I'll talk about a little kind of back of the envelope calculation and graph you can make that I tried to make, but I was having trouble with. But I hope to go through it, and that'll be part of my future work. And I'll conclude and talk about the future directions for the project. So what's the point of this thing that I'm talking about? So what's the best wavelength for gravitational lensing? So, a star, according to Wien's law, a star radiates at a peak wavelength depending on its temperature. Well, that's great and all, but as it goes to farther and farther distances away from you, it gets more and more redshifted. So that wavelength is going to go pretty far, significantly redder than its intrinsic peak wavelength. So I'll be looking at where's my starting point? I need to figure out what I need to even observe and what wavelength. How far can we see using gravitational lensing? So, telescopes have certain limitations, as all of them do. And so I hope to at least clarify how far we can hope to see in terms of the redshift parameter, Z, using the data that I have. And then another question I had, if you're talking about, early universe, you have to talk about population 3 stars, which I'll get to later if you don't know what those are, but they're theorized to be dominated in the early universe. So if you want to talk about the early universe, you have to talk about population 3 stars. And I hope to discuss how you go about doing that. So here are some definitions that when you're talking about gravitational lensing you use. The source obviously is just the light that you're trying to observe. The deflector is or they also call it the lens, is the galaxy cluster or galaxy group that's deflecting the light around and making it to your eye or your telescope. Weak gravitational lensing, I'm not going to be talking much about that, but strong gravitational lensing is mass overdensities create multiple images of source, and you'll see that on the next slide. And you can think about strong gravitational lensing as a transformation from 2D coordinates of a particular light ray, so the image plane, to another 2D coordinates where the light ray would be if it wasn't perturbed, so the source plane. And this is just a lens equation describing that diagram with the, what alpha is right there based off of the distance from the deflector to the source and the distance from the source to the observer. And then I also have this mu, which is the magnification, which for a local, for a local point source, it's just the determinant of the magnification tensor, which you see right there. And gammas are shearing parameters, and kappa is the projected surface mass density. And so this is how these two pictures helped me figure out what gravitational lensing was, because I really didn't know anything about it. So this is an actual image of gravitational lensing, and then this is an analogy that I found with a candle and glass perturbing the light. So in the top left of each picture, you see just the source that you're looking at with no lensing effects. In the top right, you see what they call a quad image, which the image is projected around the lens 4 times. And so you can see the blue image around it, the lens 4 times. And you can kind of see it over here. But the glass is obviously in the way, but there's 3, and then the 4th one will be over here. The bottom left one, you see this Einstein ring. It's incomplete, obviously, but over here you see a much cleaner one. And then bottom right, you see what they call a double image. And it's just, this is hard to see in the galaxy, but there's one right here, and you can kind of see one over there. So these are the kinds of effects that gravitational lensing can have based on the alignment of the source, the lens, and then you. So a couple papers that I read about the state of the research during this year. Actually, by the way they sounded in the papers, it's a pretty exciting time, because I think at the beginning of this year, Report et al. 2014 reported the first analysis from the Hubble Frontier Field Survey, which looked at objects at high redshift. And they looked at, or they think they found a high redshift candidate about z equal to 8. Zhang et al. 2014 used Lyman break techniques to estimate redshift, high redshifts. I'm not exactly sure what Lyman break techniques are, but I know I can maybe show you a slide if we have time at the end, but it basically is used just to estimate the redshift through some programming and some analyzing the Lyman break. And then Rydberg et al. 2014, I think this was like last month, searched for population 3 galaxies at high redshift using the Clash survey. And they found 5 population 3 candidates based on their analysis. And so here's kind of the approach I took to figuring out what redshift I should look at, what z is possible, like what's the highest z we can look at with the given telescopes. So after getting a magnitude, after reducing the data and getting magnitudes for multiple wavelengths, and they use this AB magnitude, and I didn't know what that was, but apparently it's just the reference point is 3,631 Janskis. So I guess it's not that different than just another reference point. But yeah, so they find AB magnitudes. And so to find an optical wavelength, you would use, to find the optical wavelength, I made a magnitude versus wavelength graph, and found where I graphed the galaxies magnitude versus redshift, magnitude versus wavelength, and then I also graphed the limitations of the certain filters of Hubble, which is the data that I used. And so I figured out which, based on where, if the limitations were higher than the, if the magnitude for the limitation magnitude was higher than the magnitudes of the galaxy, I knew I could accurately know those magnitudes. If it was above it, then I couldn't know it because the telescope only has a certain magnitude it could be reliable at. And so I figured out a wavelength I could observe. I could use a certain filter I could use the data at, and then I graphed a magnitude versus redshift, or not calculated, I graphed the magnitude versus redshift plot to show a trend of the magnitudes, and also to verify the highest Z of the given data set. And then I wanted to go through a couple of properties of population 3 stars and how one would calculate the magnitude of that galaxy for a certain redshift, and then based on, again, the limiting magnitudes of the telescopes, find how far we can see. And so this is the galactic lens that I used. It's called Able 2744. This is a composite color image made from optical ACS images and the WFC3 140 wide image. And it's a galaxy cluster at a redshift of 0.008, and you can see the RA index right there. These are probably the most important galaxies in the data set because they're at the highest redshift. So most of the data set, the galaxies were estimated to be about 7 to 8. There were some 6 to 7, but most of them were 7 to 8 redshift. But these two were taken to be about 10 to 10.5 redshift. So these will have the most effect on how far we can see, the highest redshift we could see given the data, the telescopes. So just going over some other reduction that how the data was reduced. So the data was taken with the WFC3 instrument on the Hubble Space Telescope from October 2013 to July 2014 with the filters 105 W, 125 W, 140 W, and 160 W. And this data was processed using a modified APSIS package, which is an automated pipeline that they call A+. And this allowed for the capacity of processing WFC3 data and aligning it with the ACS data, which I didn't really need to use, but it does that. And also the calibrated images that you saw were received from the WFC3 fit image pipeline. Okay, so this is the graph I was talking about earlier. It's magnitudes going dimmer as you go up, and wavelength getting bigger as you go to the right. And the limitations of certain filters are in yellow, and the two galaxies I talked about earlier, the ones at high redshift, are in green and blue, and each of them have the corresponding error bars. And as you can tell, there was really only one filter I could use because all the other ones were far too dim for the limitations that the filters had. So I took the optical wavelength to observe the the galaxy's at to be the 160 W, or 1.545 microns, which is that last point at the end. So once I figured out the optical wavelength, I graphed the magnitudes for the rest of the galaxies in that filter versus the redshift. And this is where I kind of got a little bit confused, because if we go back to this slide real quick for the equation for magnitudes, magnitudes will go as the negative log of the flux, and flux is a function of distance, which is a function of redshift, right? So it should be something, log to the something. So I was expecting to see a log curve, and there was a pretty heavy scatter with this data. One of the things I contributed it to was that I thought when I'm doing this, I'm assuming that all the galaxies kind of have the same number of stars. And so I think if I go back and look at, okay, now how much number of stars are in these galaxies, that'll put them on different parts of this graph. So say like this group had a greater number of stars because it's brighter, then it would be a whole different log fit to that group of galaxies. And then this also just confirms that the farthest we could see with the data that was given was at 10.5. So then, if we want to talk about the early universe again, we have to talk about population 3 stars, right? So here's some general facts about them. In the literature, they called them a lot of them first stars, because they're theorized to be the first stars that were born. They're mostly metal-free. The original ones are theorized to be metal-free stars. The temperature is about 10 to the 5 Kelvin, and I actually had a really hard time finding the luminosity of one, but I read that it was close to the Eddington limit, and that the mass was theorized to be about 300 solar masses. So I calculated it to be about 9.9 times 10 to the 6 solar luminosities. And then based on the temperature, I found an optical wavelength to observe these population 3 stars. So now we have an optical wavelength to based on the temperature, we found the peak wavelength, right? So now to find the optical wavelength we want to observe at, I took from Reidenberg et al. That population 3 stars are thought to form less than or equal to Z15. So I just took the maximum it could be, just why not? And I found that the thing you would observe at to find a galaxy that's at Z of 15 to be about 0.46 microns. So after assuming we have certain Z values, you can then calculate the distance based off the Hubble law up there. And again, it's not just the simple Hubble law, because that's only for low redshift. I made that mistake first. You have to use that one for values greater than 1. And then once you calculate the distance, you can calculate the flux. You then have to convert that flux to Janskys to get it in, to then use it to get the AB magnitude, which then can be calculated by, again, the same equation we saw earlier. And by the way, this mu is the same mu that we saw earlier with the magnification. So the magnification, the magnitude scales as the log of the magnification. I had trouble doing this, and that's why I don't have that graph now. That's part of my future works. I think what I was messing up on was converting from just SI unit flux to Jansky flux. So for my future work, I had to go back and look at that and see where exactly I messed up on, because I was getting negative magnitudes, which obviously isn't right. So in conclusion, based on the data given, the optical wavelength was found to be 1.545 microns, which is the 160 wide HST filter. The magnitude versus redshift graph was the magnitude versus redshift graph, assuming the optical wavelength, which is 1.545 microns, verified that from the data that the redshift was 10.5, and however the fit didn't work out. So that's one thing I'd have to go back and check also, and that the maximum redshift for a POP3 star wasn't accurately found, which is one of my questions that I wanted to answer. But I kind of went over how to do that, and hopefully I'll do that in the future work. So again, the future works I kind of list from like what I thought would be maybe the easiest to the hardest. So to figure out why there's an error in the magnitude versus, that the data error does not match the limiting magnitude that it was observed at. So if we go back there real quick, why this error isn't reaching the limiting magnitude. That's something I was a little confused about, because if you observe it, you put error bars on it, but it's not in the limiting magnitude range. That's something I was confused about. Updating the magnitude and redshift graph to include, to somehow incorporate the number of stars that each of the galaxy has, so you can kind of maybe make multiple log fits, so that it's a better fit overall. Calculating the limited magnitude for JWST would be a big thing to do, I think, because you can kind of give a general idea of how far we'll be able to see with JWST when it's online. Again, you can then use the limiting magnitude for JWST with your calculation that I described in the discussion to find a new maximum redshift that we'll be able to observe at once JWST is online. And I think that would be a big help for someone who's about to use JWST for that reason. And then if I could probably make, the last two are just kind of thoughts I've had, like long-term plans. Like you could use JWST once it's operational to explore even higher redshifts than what we can do right now with HST and Spitzer. And then confirming that population 3 stars are actually, they actually exist, because from the literature I went through, I couldn't really find anything that verified that population 3 stars existed yet. So that could be a career project. So, and then my references.
Okay, time for questions.
Yeah.
Okay, so if you go back to your graph with your limiting magnitudes, that one. Okay, so the yellow line, you say M5 sigma.
Yeah.
When you say 5 sigma, do you mean you took the traditional limit and then added 5 sigma to it to get the absolute dimmest?
So what I understand is 5 sigma when they're talking about limiting magnitudes is that you take the signal to noise ratio to be 5 for a given telescope, and you solve it for the magnitude. So that's the magnitude at which that telescope can measure 5 signal to noise.
Okay, and then brighter than that would be better signal to noise.
Right, because it's going to be dimmer. Right.
Okay. And then second question, when you were finding the magnitude, the apparent magnitude of your population 3 star, you're looking over really large distances. So in cosmology, there's different distances that you need to be worried about. which one were you using? Because that can occasionally be a problem.
Well, I thought it would be I just took the Hubble distance and then used that as the distance scale.
Were you using co-moving distance or luminosity distance? That's my question.
That may be something I need to look into further. I'm not exactly sure.
That may be what's happening.
Yeah.
So that could be a really easy fix.
Okay.
Yes.
So, what's the exact relationship between magnitude and redshift?
The exact relation? Okay, well, I didn't write it on here, but what I basically took as the relation was you basically plug this into here and then plug this into here, right? After converting, because this will be, so when I first tried to do it, I started with SI units, right? And so I found a flux in SI, and then I tried to convert this flux to the flux in Jansky's, and then you just plug this F into here, and then for a given magnetization of a galaxy, you could find the magnitude, AV magnitude. So it's just a matter of substitution.
So if you go to the plot where you're plotting magnitude versus redshift, right, so that one. So, like, even though these error bars are comparatively low, especially for the brighter magnitudes, the fit that you have, is that a theoretical fit or is that?
Yeah, that's just the a log fit that I fitted against that, which I assumed it would be because of the relation between magnitude and redshift.
So my question is, so for this log fit, what did you take inside the log? Did you put in the values of your redshift for a particular case, or did you have a functional for just a redshift relation?
Are you asking what, like, how did I come up with this fit? Is that what you're asking?
Yeah.
Yeah, so let's see. Yeah, I think I tried to scale it the best I could. I think it was another thing of I didn't know. It had something to do again with the converting from Jansky's to SI units for flux. So this was basically right. Like in terms of scale, it's right, but the exact numbers I think are a little off, like how high or low it is. But it's still the basic idea is that it's nowhere. These plots are nowhere near in a log graph. So.
Any other questions?
What is the typical value of mu?
Well, in this data set that I got, I averaged it to be about 2.9. So most of them were around 2.5. But then you'd have a couple that raised the average up a little bit. So you'd have a couple in 3, like maybe 2 or 3 and 4. And then there was one that was like 14. So it really varies. And that was probably like 24 galaxies.
This is like the modification of the gravitational lens?
Yeah. Yeah, so if you go back here, yeah, it's this equation right here. And so this is the projected mass distribution into shearing parameters. And I guess that's how you calculate it.
So do you know all these parameters necessary to calculate mu, like from observation?
I don't know them I didn't know them for the data set. I just it just was given, but I assume each galaxy has a specific shearing effect for a specific lens and the mass distribution of the lens.
More questions? Okay, I have a few questions.
Okay.
Let's see. Oh, on slide 4, do these equations make sense to you? Any of them?
Well, I didn't show it because it was a little mathy, but they had the inverse where I found this equation, which was this paper right here, they have the Jacobian of the.
So I just want to know if they make sense to you, if you look through these and make sure that you understand them. What's this thing here?
Yeah, that's the only part I wasn't sure about, but I understand like this right here. But this has something to do with the Poisson's equation with, so there's another equation that says the Laplace, or the Poisson's equation.
What's this theta there? Can you point to that?
Yeah, it's right here. So it's the.
That looks like that little funny.
I guess it's a vector.
Is that the same as that theta?
I assumed it was like the magnitude.
Okay, and alpha, I guess, is the magnitude of that vector.
Yeah, right. And so,
oh, I see the unit vector.
yeah.
Okay. What's this kappa? Do you know what that is?
Yeah, that's the projected mass distribution of the lens.
Okay. So you didn't go through in detail to verify all this, but you found it in papers.
Yeah, and
it seemed plausible.
Yeah.
Okay. I thought you mentioned something about some papers where they found some POP3 candidates. Was that, or did I miss that?
Yeah, so in this one they found.
It was recent.
Yeah, the Rydberg one. It was, they found 5 POP3 candidates.
Okay.
But I think they found them a different way than I did. That's why I couldn't really like use that as a way to find them. So, and it was also, I also found it weird that it didn't say it was published anywhere, so I didn't take it. I took it, at face value. So
Okay. Go to slide 7.
Oh. All right.
Let me see. Yeah, what do I mean by slide 7? Because I'm using your
Yeah,
the ones that you had.
I hit those.
Let me see. Go to the picture of Abel 2744.
Yeah, so JD3, that's one of the ones I emphasized, and JD2.
Okay, that's what I was going to ask.
Okay.
They're right there. Okay. And then go to the next slide.
Okay.
Okay, so the object that you're highlighting, I think, is in between these 2 red lines, right?
Yeah, so this is the center of the
Yeah.
picture.
Yeah. And so I take it that's the object, right?
Yeah.
And you can see it in the 160.
Yeah, so that's what, and that's why I thought, again, what based on the graph, the magnitude versus wavelength graph, and these pictures, I thought that the 160 filter would be the best, based on the data.
And this one looks like there's something there.
Yeah.
Okay, but it looks like you can't see the object very well if at all at shorter wavelengths.
Yeah.
Why is that?
See, that's one of the things I want to go back and check, because that's why on this graph, the magnitudes is way higher than the limitations of the filter, which I thought was very confusing.
So why is the object faint at those wavelengths? It looks like it's getting brighter at longer wavelengths. I think you said something about Lyman break. Is that related?
Well, in like Zhang et al., they estimate the redshift based on the Lyman break technique.
Okay. What is the Lyman break? You know,
I have the paper right here. We can.
well, no, that's okay. I'm just asking you if you know.
No, it was kind of confusing.
Okay, you don't know what Lyman break is. Okay, that's fine. You should look that up and figure that out.
Yeah.
And I think that what's happening is at the redshift of these objects, you're short where the line to break for wavelengths less than 160. And so the object is going to be faint because all the light's absorbed.
Okay.
It's all absorbed by line of sight hydrogen, right? That's in a ground state and it gets absorbed by the radiation because it's short word of the line continuum, 912 angstroms, and the rest are.
Okay.
That's what the line is.
So that's why that you can't really see it in the.
Yeah, so these are called dropout galaxies, and this is the original way people found IZ stuff.
Okay.
You can't take a spectrum. This is so faint, right?
Right.
But you can collect enough light to get to see something in the broad band, and so you look for the line of break, which is the redshift at 912.
Oh, okay.
Okay, but you should look that up and actually, don't take my word for it. Go to slide 12, which, let's see what that means. Slide 12. There we go, conclusion. Okay. No, go to your slide 12. I switched to something. Here we go. The yellow there, that 5 sigma, what observatory is that for?
It's the Hubble Space Telescope.
Did you calculate that?
It was in the data. I
5
looked it
sigma?
up. I looked at
Okay.
the 5 sigma.
And 5 sigma for what exposure time?
Different exposure times, I think. Or
So that's a problem, right? If you want to figure out the ability to observe something, you have to
well, no, yeah. So it
take
yeah.
exposure time, because
It
you
must
can
have
always
been the same.
expose for longer and see fainted, right?
Right. So it must have been the same exposure time then. I'm not quite sure which one it is. I just like looked it up as
Right, but if you're trying to answer the question, how far can we see or how faint can we see?
right.
You have to pick a set of facilities and then a set of wavelengths and then a set of exposure times, or maybe the maximum exposure time
Mhm.
to get the best sensitivity.
Right. Okay.
Okay, and then the next slide, you said if you took account of the number of stars in the galaxy, maybe you would find that they would have more similar magnitudes. Is that the point?
Well, I think that you would find if you figured out like you're assuming here that they're basically all on the same bit, right? But if you take the number of stars for each galaxy and you find like similar ones, then you could find then each of those numbers will be on a separate log
Yeah.
fit.
Unfortunately, I think that to normalize for number of stars in the galaxy, you probably look at brightness and estimate the number of stars,
Okay.
right? So that it's hard to independently know what the number of stars is.
Right. Okay.
Anyway, that's all I had. Were there any other questions? Okay, if not, right here.
So when you observe a galaxy, how do you know that it consists of a population of 3 stars? You cannot take a spectrum, right? For such faint objects.
Yeah, that's a good question because I remember reading in that Rydberg paper that like they use the same Lyman. I think it's a similar thing. They call it Lyman alpha break, and so they use this technique to find the redshift. But they did talk about. I think they talked about talking about the composition of the stars. So I'm not. That's
Yeah, but how do we detect this?
How would you detect population 3 stars?
Yeah. How do we differ them from?
Well, it sounds like you're not sure.
Yeah.
Okay, so just say you're not sure. Always a safe answer. Okay, let's then take a guess.